All right, so let's see if we can establish a local error estimate for splitting methods, but now applied to nonlinear ordinary differential equations. Okay, so well, splitting methods for nonlinear ODEs. Okay, so let's state the following theorem. So the theorem states that if you're given a decomposition of a vector field f into f1 plus f2, right, then the splitting method given by the composition of the individual exact flow maps of the f1 and f2 vector fields, right? So the exact flow of the f2 vector field with a time step h composed with the exact flow of the f1 vector field with time step h, right, has local error, which is the following. So the local error for initial condition y with time step h is equal to h squared over 2, the bracket, okay, what is called the Jacobi-Lie bracket of the two vector fields, f2 and f1, plus something which is big O of h cubed. Okay, so this is very, very similar, it's like, to the result we had in the linear ODE case. If you recall, in the linear ODE case, the local error term, it's like involves the matrix commutator of it's like of two matrices, okay, and the matrix commutator, it's like measures the extent to which these two matrices commute or fail to commute, okay, and the same thing happens here, okay. So when you take the Jacobi-Lie bracket of two vector fields, then you're measuring the extent to which these two flows generated by the two vector fields commute or fail to commute, okay. So, where again this bracket f and g, right, is the Jacobi-Lie bracket of vector fields, and it has the following sort of coordinate representation. So if you take f and g and you take the bracket of this, you get you get again a vector field, and the ith component of this is the following expression. It's the sum over k of fk dgi dyk, and in principle, it's like there's this repeated index. It's like which it's like you should think of as evoking, it's like the Einstein summation convention, but here I've explicitly written down the summation here. But you could just as easily have omitted, it's like that sum, it's like, and just sort of appealed the Einstein summation convention. Okay? All right, so gk the fi the yk. All right, so we had talked about the Jacobi-Lie bracket before, and this is a reminder of what it is. Okay, so there's a more general result that's like which basically tells you what's the next higher order term is in the error term. Okay, and this comes from what is called the Baker-Campbell-Hausdorff theorem. Okay, so more general result. Follows from the Baker-Campbell-Hausdorff theorem. Which says that the splitting error, the splitting method, which is again the composition of those two flows, where f is equal to f1 plus f2, right, has local error yh, which is equal to h squared over 2, the Jacobi-Lie bracket of f2 and f1 plus h cubed over 12 f2 minus f1 again bracketed with f2 comma f1. Okay, so and the basically this series, it's like sort of continues, and there are expressions for each term in the series. But the thing it's like to be mindful of, if you will, is that you see it's like in this term, which is cubic in h, right? There is the Jacobi-Lie bracket of something with the Jacobi-Lie bracket of f2 and f1. Okay, and this is true of all the higher order terms. It's like in this Baker-Campbell-Hausdorff theorem. Okay, so it's so what basically happens then is that if the two flows commute with each other, which is to say that the Jacobi-Lie bracket of these two vector fields vanishes, right? So this term will vanish, this term will vanish, which means the whole thing will vanish, and basically the same result which was true, it's like in the linear ODE case, which is that if the two matrices commute, right, then the splitting method is exact. The analogous thing happens in the nonlinear ODE case, which is that if the Jacobi-Lie bracket of the two vector fields is equal to 0, which is to say that their flows commute, then the local error of the well, actually the error of the splitting method is 0. It's like, and so the splitting method is exact if the underlying flows commute. Okay, and then if not, then the result basically tells you that the splitting method is only order 1. Okay, so this is of course directly analogous. It's like to what you have. It's like in the linear case, except that in the linear case, it's like you had the matrix commutator showing up, and in the nonlinear case, you have the Jacobi-Lie bracket of the vector fields showing up. Okay, so let me stop for a minute.